Hi guys, welcome back to Data Every Day. Today we're looking at a data set of Michelin-starred restaurants, and we're going to basically try to be predicting the star rating of a restaurant based on a series of features. So you can see there's three different CSV files, the 1-star CSV, 2-star CSV, and 3-star CSV. So we're going to put them all into one data frame, and then we'll label them based on which CSV they came from. Alright, so let's get started. Given data about Michelin-starred restaurants, let's try to predict the number of stars of a given restaurant. And we'll use a logistic regression model to make our predictions. So this will not be another simple video. I have NumPy and pandas. I'm going to be using regular expressions and the standard scalar and train test split function from sklearn for pre-processing. And then we will use logistic regression, like I said, for our model. So I'll go ahead and import that. And why don't we just load in our data? Well, we can't just load in one, we have to load in all three. So, well, how about we have 1-star df, 2-star df, and 3-star df. And I'll go and grab these CSV files. So each one will be pandas.readcsv and this. So this is 1-star, this is 2-star, this is 3-star. Alright, it's probably the wrong 2 stars. So stars and stars. Alright, so now let's take a look at them. 1-star df looks like this. I'll just do head to keep it simple. Then we'll have 2-star df, and we'll do 3-star df. Alright, we just want to make sure that these all have the same columns: name, year, latitude, longitude, city, region, zip code, cuisine, price, and URL. And looks pretty good. I think they all have the same number of columns, and we just want to make sure of that because we're going to be putting them into one single data frame. So let's try pre-processing. And what I'm going to do is basically add a new column onto each one before I combine them. So 1-star df, I'm going to call this column stars, is going to be a series of zeros. And even though it's a 1, I'm just keeping this at 0, 1, 2. So 1 star will be given by 0, 2 stars will be given by 1, and 3 stars will be given by 2. And to have the zeros spread through the whole series, I'll specify the index will be 1-star df.index. Alright, and we'll do the same thing for the other two. This will be 2 and 2. And this will be a 1. And the last one, this will be 3 and 3, and this will be a 2. Alright, then we'll create a combined data frame. That will just be the concatenation, so pandas.concat of 1-star df, 2-star df, and 3-star df. And we're combining them on axis 0, so on top of each other. And what I'm going to do after that is shuffle them, because if I stack them on top, all the zeros will be on top, then all the 1s will be there, and all the 2s will be there. So let's shuffle them by sampling. Frac equals 1.0, so this is the fraction of the data that we want to sample, and we want to sample all of it so that we just shuffle the data. And then reset index after that so that we keep the same indices. And we're going to say drop equals true to prevent the old indices from becoming a new column. Alright, so let's look at combined df. And this is going to be our data. So you can see the stars has been shuffled. There's 0s, 1s, and 2s in here. And now we can start figuring out how to deal with this. So because let's see. All right, what I'm going to do is actually split it now. I'm going to split off what we're trying to predict. So y is equal to combined df sub stars dot copy. So just a copy of this column here. This will be our labels. And then x is going to be combined df dot drop stars from axis 1. Alright, so y looks like this, just the label column, and x is everything except the label column. Now we can drop a lot of stuff from x. So how about this? First we'll deal with the unneeded columns. There's a bunch of features here that are not going to help us. So, first, the name is not going to help. The zip code is probably not going to help, and the URL is definitely not going to help. Although, with some very creative methods, we may be able to actually visit the URL and gain some more features based on that, but we're not going to do that for today. So, let's see. X.drop name zip code URL axis 1. Not, yeah, that's our x. Alright, so we'll drop those, check it out. Now we have a smaller data frame, but these are useful features. Alright, now we see we have at least some missing values, so let's check those out. Missing values. So I'm going to sum across the rows, is na.sum, so we get the number of missing values in each column. And we can see city has only 2 missing values, but city is a nominal feature, so this isn't a problem. We'll just one-hot encode it, and those examples of missing values will just have all zeros in the one-hot columns. But price is an ordinal feature, right? Because it counts up. There's low price and high price. So we can't just, we have to actually do something here. And I think the best thing to do would be to look at the value counts of the column. So how many of each unique value do we have? And you can see most of our restaurants have $4 signs for price. This is the mode. So what we could do is just impute all these missing values with the mode. So let's say, okay, x sub price dot mode looks like this. So what I want is just the string. So what I'll do is sub value dot values and then sub 0. And that will give me just the string that I want to fill in with. So I'm going to fill in, so x sub price dot fill in a, and we're going to fill missing values with this. And so that would effectively, you see up here we have this missing value in the second example. It has been filled with $, $, which is the mode. And the reason that we can't just drop these is because we don't have a lot of examples, and there's too many of them that are missing. So we have to figure out how, we have to impute them some way. So it's not ideal, but it's probably the best thing I can think of to do. So, alright, that's going to be our new column. And now if we were to look at the missing values again, oh sorry, x not data, we only have these 2 in city, and like I said, that will be fine because we're one-hot encoding that column. Alright, so let's start encoding. So I'm going to take a look at the unique values in each of the categorical variables. So I'm going to make a dictionary that maps a column to a list of the column's unique values for every column in x.columns if x.dtypes subcolumn equals object. So this part's saying only get the columns that are non-numeric, and then create a dictionary that maps the column name to a list of the unique values in the column. And if we look up at the data, you can see we have city, region, and cuisine and price. These are our categorical columns. So let's look. In city, we have a bunch of unique values, looks like. And we're going to scroll down. We have region here. Region has not as many, but also a good number. So these will both be one-hot encoded. In cuisine, yeah, has a good number as well. And price here, this is our ordinal variable. We're going to ordinal encode. So, let's start with this, since this is the simplest. We will create an ordering. So price ordering. This is going to be all the unique values of price, but in the order that we want them. So $sign is first, then $2 signs, then $3 signs, then $4 signs, and last is $5 signs. So this is our ordering. And the cool thing about this is now we can index one of these in the ordering to get the numerical equivalent in our ordinal encoding. So all we have to do is say x sub price equals x sub price dot apply. So we're going to apply a lambda function here that takes in a price, which will look like one of these, and it's going to spit back price ordering dot index price. So if we look at what this looks like, I'm just going to run that part. I didn't define price ordering. If I define it and then look at what this looks like, you can see originally, here, let's get this up here. Originally we had these $sign values, and now they've been converted into the numerical values based on the ordering that we specified. Alright, so that will be our price column. And now, if we look another, well, let's just look at the data actually. You can see price is numeric, and now we just have to deal with these ones. So I noticed when I was scrolling through here that all the way at the top, under city, we have this issue, which is we have a bunch of zip codes, looks like, attached to the end of some cities. And this wouldn't really be such a problem, but we have duplicates here. It's distinguishing two areas of Sao Paulo from each other. And here as well, here as well. So we want to count them as the same. Because we don't have that many examples, and we want as much overlap between these as possible, so our model is able to pick up similarities between examples. So what I want to do is just go ahead and strip off anything that looks like that. And for this, regular expressions would be a good method. Now, if we can ensure that these zip codes all have exactly the same length, we wouldn't actually need to use regular expressions. We could just go back from the end of the string and chop off that amount. But I'm going to just use them because it's nice. So regex101.com is a fantastic way to test regular expressions. If I go ahead and grab one of these, and I'll paste it in on regex101, this is our string, and we can now type in regular expressions up here to try to capture various aspects of the string. So what I want is $sign signifies end of the string, end of the line. So we want to start by working back from the end. So \d is digit characters, and I put a plus to signify any number of them in a row. And this is saying so any number of digit characters and then the end of the line. And that's what we have here. And then before that, it's a space, a hyphen, and a space. And that will capture exactly what we want. So here, right here, our regular expression, we're going to use this in our code. And so all we have to do is, okay, we call, so re, that's regular expressions, I imported that at the top, dot sub will substitute a regular expression with another string, and we have to specify the string we're processing. So we're going to apply this to the city column. So x sub city is going dot apply a lambda function that's going to take in some, let's call it a city, and we're going to call regular expressions dot substitute on city, but we're going to pass in the regular expression, which is this thing that we got from regex 101, and then what we want to replace it with. And we want to just get rid of it, so we're going to replace it with the empty string. And we're going to do this for each city in city. What's the issue here? Oh, right. Okay, so there's actually, like we saw earlier, there are some null values in this NaN. So we don't want to apply this to the null values. So all we have to do is if string representation of city is not equal to NaN, and otherwise, if it is NaN, we'll leave it as it is. And city is not defined. Oh, what happened? I put this in the wrong lambda function. It's down here, right? Okay. So if string representation of city is not equal to NaN, and if it is, we'll leave it as it is. City, not X. Okay. Alright, so that actually got rid of all of the zip codes. So that's going to be our new column. Alright, so now we can work on one-hot encoding. So we just have these three columns to do. So we're going to make a function called one-hot encode. One-hot encode. It's going to take in a data frame, a list of columns, and a list of prefixes. And so before I create it, I will just demonstrate what the getDummies function does. It will take in a, let's use cuisine, okay? Takes in a column and a prefix, which I'll leave as none for now. And basically it takes each unique value of the original column, so the cuisine column, and makes a new column out of it. And it will encode a 1 in a spot where the original the original value was that column. So you can see example 3 has a 1 in the Thai column. If we look up at our data, you see example 3 had Thai as its cuisine. So that's essentially what this does. We can also include a prefix, C for cuisine, that will just add a C to the beginning of each column name. And the prefix is useful because, for example, we're going to be one-hot encoding city and region. And as we can see, they have duplicate values. So if we one-hot encode them separately, we'll have the same column name in two places. And we don't want that, so we'll include a prefix to distinguish them. Okay, so we'll start by creating a copy of our data frame. And we'll create the dummies. So we're going to make the dummies, actually, sorry, we're going to iterate through the columns first. So we're going to iterate through the columns and prefixes simultaneously. So to do that, we'll say for column prefix pair in zip of columns and prefixes. And zip will just pair up columns and prefixes element-wise into tuples so that we can iterate through them simultaneously, tuple by tuple. And now we can say dummies is going to be pandas.getDummies for the specific column we're on, df subcolumn. And we'll include the prefix here as the specific prefix that's been matched to the column. So they go in a pair, right? And then we're going to concatenate using pandas.concat the original data frame and the new dummies columns that we've created. And here we specify axis equals 1 as we want to put them side by side. Then when we're done, we will drop the original column from which we created the dummies. and then we'll return the data frame. Alright, so let's one hot encode x equals one hot encode. So we'll pass in x. We'll pass in the columns we want to encode, which will be city, region, and cuisine. City, region, and cuisine. And then we need a list of prefixes to go along with it. So how about CI for city, RE for region, and CU for cuisine. Alright, we run that, take a look at x, and now you can see we have all these one-hot columns. We actually have 277 columns in total, but we can see that the entire dataset is now numerical. And that means we can go ahead and feed it right into our model. One last step though is let's scale the data. So scaling and splitting. And we'll create a standard scaler. This is imported from sklearn, which will give each column mean 0 and unit variance. So x is going to be scalar.fitTransform x. And if we take a look at x after that, you can see it's now just a scaled version of this. If I want to view it as a data frame, you can see it's like before, but now we have these. Yeah, each column has mean 0 and variance 1. And we're going to split it into a train and test set. Xtrain, xtest, ytrain, ytest equals train test split xy with a train size of 70%, and we'll include a random state, and this can be anything really. How about 40? Alright. And now we will training. So I'm going to do what I did in my last video, which is create a bunch of models with different regularization strengths. They're all logistic regression models, and then we'll compare the how the regularization strength affects the model's performance. So I'll create this empty list of models that we'll add models to, and I'll create a list of C's. So C is the inverse regularization strength. So the lower the C, the more regularization we have, and the higher the C, the less regularization we have. So we can initialize this to just be 0.01, 0.1, 1.0, 10.0, 100.0. And then for I in range, length of C's, so basically for each C, model, actually I can just say for C in C's, right? Model equals logistic regression. And we specify C equals C. And then we're going to fit the model. No, actually no, I needed the, this is why I needed the I. Okay. Model equals logistic regression. C equals C sub I. And then model.fit on xtrain, ytrain. And then we're going to append, wait, what am I talking about? I actually didn't need the C sub I. Whatever. Models.append model. So what we're doing is creating a new model with a given C value, and we're going to do it for each one. And then we're going to fit it and append it to our models list. So at the end, our models will be filled with logistic regression models that have been already trained. Alright, so now we'll create, I'll say results, and we'll create a model accuracy list, which will just take the score on the test set, xtest, ytest, for every model in models. So this will be a list of the scores. And then I'll print out each of the accuracies. So I'll just paste this in. This is saying we'll print model accuracy, show the C we're using, and then the actual accuracy for that model. And we take a look, it looks like as we decrease the C, our performance increases. So let's try a few more C's. Let's add some more over here. 0.001, and how about 0.0001? So all we have to do is add 2 more at the end here. This would be 5, and this would be 6. Oh, I didn't train it. There we go. Now we'll check it out. Let me just indent these so that they're matched up. Sorry, I just want to make these nice. So these go 2 spaces, this goes 1 space, this goes 1 space, and then all of these get 1 more space. Okay. Delete these. Okay, so it looks like once we get below 0.01, we reach our sort of plateau. And that low values of regularization, sorry, this is high regularization, right? Because we have a low C, that's high regularization strength. As the regularization strength increases, we have a better performance on our model. So that tends to mean that our model was overfitting before the regularization. Alright, so I guess that sums up today's video. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. Thank you so much for watching. I'll see you guys tomorrow. Have a fantastic day.